the physical limits of the universe. To see those limits tested, we have to look inside a dying star. For billions of years, a star survives by playing a high-stakes game of tug-of-war. Gravity relentlessly pulls massive amounts of matter inward, while the intense heat of nuclear fusion pushes outward. As long as the star has fuel to burn, these two forces remain in a perfect, stable stalemate. This chart shows the evolution of central temperature and density for massive stars. Following the line upward reveals a continuous contraction. Each time the star depletes a nuclear fuel, it shrinks, growing hotter and denser to ignite the next heavier element. Eventually, the star fuses lighter elements into an iron core. But the fusion chain stops there. Creating iron consumes more energy than it produces. Because no new energy is being generated, the outward thermal pressure drops to zero. With nothing to push back, gravity takes complete control. The star's iron core collapses in on itself in less than a quarter of a second, reaching speeds near 25% the speed of light. This total failure of internal support creates a gravity bomb, primed to detonate. When thermal pressure fails, the universe relies on a mechanical defense at the quantum level. It's based on the Pauli exclusion principle, a rule dictating that certain subatomic particles cannot occupy the exact same state and physical space at the same time. As atoms are crushed inward, their electrons are packed so tightly they repel each other. This creates electron degeneracy pressure, a quantum shield that halts the collapse and leaves behind a glowing, ultra-dense core known as a white dwarf. A white dwarf is roughly the physical size of the Earth, yet it packs in the mass of hundreds of thousands of Earths. But for stars much larger than our Sun, even this quantum shield breaks. Gravity squeezes the core with such intensity that the electrons and protons are forced to merge, forming a dense ball of pure neutrons. The outer layers of the star are still rushing inward. When they hit this newly formed rigid wall of neutrons, the material bounces off. The sheer force of the rebound triggers a colossal shockwave that blasts the rest of the star out into deep space. This simulation shows the assumed heat signature of that resulting core collapse supernova. It's an explosion so energetic it briefly outshines entire galaxies. When the dust clears, the remaining core is a neutron star. It contains more mass than our Sun, packed into a sphere only about 10 miles across. It is matter pushed to the extreme edge of existence. Even neutron stars have a breaking point. Physicists calculate a threshold called the TO